Hi, my name is Brittney Gorman. Today I will be presenting my work on depth correction and height estimation for 3D SIMS depth profiling images. In this work, we depth correct 3D images of cells in order to get a better idea of what the organelles within those cells look like, both in their lipid composition and size. In many diseases, lipids might abnormally accumulate within organelles, such as Niemann-Pick type 2 disease, where cholesterol accumulates within the late endosomes and lysosomes, and those organelles subsequently grow in size. Therefore, we have developed techniques in order to image lipid composition with a high-resolution SIMS device, where we incorporate non-abundant isotopes into lipids of interest, such as sphingolipids and cholesterol. We then image the same region on the cell multiple times in order to get a 3D depth profiling image of the cell. However, this image has distortion due to the stacking of 2D images to create the 3D image. And so we have also developed techniques in order to depth correct the image, given that we are only given specifically the data collected with the SIMS. The first step is to predict the height of the cell that we are trying to depth correct. And so in this, we utilize the sputter depth in order to correlate that with the pixel intensities within the secondary electron images. So the first step is to detect the border in the last depth profiling image. Find that same border in the first image and set that border to equal the height of the sputter depth during the depth profiling experiment. We then calculate the height of the bottom image by having it equal the same distance, same sputter depth from the top image. When we incorporate this into our morphology reconstructions, we get height predictions that have a little bit more slope to them that indicate or that are closer to what you would expect from a real cell versus a very flat surface that has some contour to it. We then tested this approach for height prediction using focused ion beam secondary electron microscopy depth profiling, and found that when compared to atomic force microscopy topographies, we got pretty good estimations of the height predictions. In the atomic force microscopy, both of these cells were around 1.2 microns in height, and we got a predicted height of 1 micron and 1.2 microns for our algorithm. The final stage is to use these morphologies to depth correct enrichment images that show the lipids within the cell. So we took images of the N15 and O18 enrichment within MDCK cell, and when of a labeled MDCK cell that would indicate the presence of sphingolipids and cholesterol within the cell. When we look at the images before depth correction, we see that we have an oblong shape of green or cholesterol enrichment within the cell. However, after depth correction, we see that that oblong shape is more round. And if we were to look at it in a 3D image, it's actually quite spherical, which would indicate that it's pretty close in the expected morphology of these lysosomes or endosomes within secondary electron images that we've seen. So therefore, we may be seeing a organelle in it. However, in order to confirm that, some of our future work will be utilizing genetic fusion proteins in order to label, incorporate distinct labels that can be detected with nanosims at the same time as we're detecting these lipids. Thank you.